start with only 1 minute late. Are you ready, Staros? Okay. So the first speaker is Naoki Sasakura, Emergence of Classical Spacetime in Canonical Tensor Model. You have 25 minutes, and there will be 5 minutes questions and answers, and I will come up and tell you when there are 5 minutes left on the clock. Please. And you have to unmute yourself.
So thank you very much for the invitation, the introduction. And first of all, I'd like to thank the organizers of this conference for this very nice opportunity to present a talk in such a difficult situation of COVID. So let me start my talk. And today, I'd like to talk about the emergence of the classical spacetimes in canonical tensor model. And this talk is based on a collaboration with Taigen Kawano. He's my student. And actually, the corresponding paper appeared yesterday, and the archive number is given here. So let me start with an introduction. And as you all know, the quantum gravity is one of the most fundamental problems in theoretical physics. And it is supposed to answer a question like how the emergence of the spacetime can be done. And there are a lot of approaches to quantum gravity, and I'm interested in discrete approaches. And in such a discrete approach, it is generally very difficult to realize the emergence of the spacetime. And typically, such an approach ends up with ugly objects like this one, a random collection of fundamental objects. But probably the universe should be described more uniformly like that. A possible scenario to circumvent the difficulty would be to regard the emergence of the extended spacetime as the emergence of the Lie group symmetry and large representation space. A simple example is given by two-dimensional sphere. And in this case, the symmetry, Lie group symmetry is the SO3. And a lot of representations are realized by the spherical harmonics on the two-dimensional sphere. This kind of algebraic manner to regard spacetime would be able to be attributed to Professor Maduro. So today, I'd like to talk about whether this scenario or in the previous slide can be realized in canonical tensor model or not. I will explain a little more about the canonical tensor model, but here I just want to say that it's a tensor model in the Hamiltonian formalism. I use a CTM for the short notation for the canonical tensor model. And it's Hamilton formalism. So when it is quantized, this tensor model has wave function. And here P is one of the canonical conjugate pair of the variables of the canonical tensor model, Q and P. And the known fact about the canonical tensor model is that this wave function has peaks at Lie group invariant value of the tensor P. So the situation, it can be described by this illustration here. So in this sense, the emergence of the Lie group symmetry is occurring in canonical tensor model. So the question here in this talk is whether this is any signs of emergence of spaces can be seen in canonical tensor model. This is the question I'd like to answer in this talk. The main results are given here. So instead of discussing psi-p, the wave function in the p representation, I want to study the wave function in q representation, which q is the canonical conjugate of 2p. And as I will explain later, this wave function is described by a certain physical system. So therefore, the computation is generally non-trivial. And I will apply here in this talk the Monte Carlo method to compute this wave function. And another thing I want to say is that because of the technical difficulty of Monte Carlo method, I also have to introduce a new parameter lambda. This is a kind of smearing parameter into the wave function. So what we actually study is this wave function psi, q, and lambda. Anyway, this wave function can be described by a physical system, and this physical system has we find that this physical system has two phases. One we call quantum, and the other we call classical phase. And from the point of view of the physical system, q and lambda are the external parameters. So the which of the phases is realized depends on the parameter q and lambda. And the name, the classical phase, comes from the following fact that the fluctuations of the variables of the physical system are strongly suppressed. I will show you the data later. And now let me put Lie group invariant value of Q into this argument. Then what happens is that Lie group invariant classical geometric spaces emerge in the classical phase. Of course, there are a lot of possibilities of the Lie group invariant value of tensor Q. So what we actually do is just to demonstrate the above facts for the emergence of the n-dimensional sphere. Here n runs from 1 to 3 from SO n+1 invariant tensor Q. So these are the summary. Now let me start with the content, and let me first explain the wave function of canonical tensor model. So canonical tensor model is a tensor model in Hamiltonian formalism, mimicking the Hamilton formalism of general relativity, more precisely what is called ADM formalism. The motivation to consider this mimicking is to include a time direction consistently in tensor model. What I mean by consistently is to incorporate this space-time diffeomorphism into the tensor model. So now the Hamiltonian of the CTM is a linear combination of first-class constraints H hat and J hat. Here, H hat is the analog of the Hamiltonian constraint in ADM, and J hat is the analog of the momentum constraint in ADM. NA and NAB are the analogs of lapse and shift in the ADM. Now, the physical state condition is given by what is usually called Wheeler-DeWitt equation. And also, we have to impose the momentum constraint to the physical state. And I do not go into the detail here, but we can show by under some reasonable assumptions that H hat and J hat can be determined uniquely. Here, H hat has this expression here, and there is one parameter R, which becomes relevant in our later discussions. This parameter is actually determined by this form from the hermiticity of the Hamiltonian constraint. Here, n is the range of indices of the tensors. At first sight, the equation looks quite difficult to solve. because of the presence of this cubic term. But what is surprising here is that there exists an exact solution for general n. The exact solution is given by this integration form. The integration variables are given by R sets of one n-dimensional vector and one scalar by children. And so here, the parameter R in the Hamiltonian constraint serves as a replica number. This form of the action here is not completely new. I mean, there is a similarity with p-spin spherical model for the spin glass. In that spin glass model, the Hamiltonian is given by this form. So if you put p equal to 3, then it recovers this cubic term. But there are some differences. For instance, the size of this variable is constrained in the spin glass case, but none for our case. And also the coupling here is a random coupling in the spin glass case. But rather in our case, the p is an external variable for the system. Now let me discuss the wave function in Q representation. This is just given by Fourier transform of the wave function in P representation. And because the exponent here is linear in P, so what you obtain by this Fourier transform contains a product of delta functions like that. It is not easy to handle this delta function by Monte Carlo, so we have to do something. And I introduce a smearing here. So lambda is a smearing parameter, and lambda making lambda to infinite corresponds to the original wave function. Now, by doing this, this difficult part, this delta functional part, becomes a sort of a Gaussian form and can be handled by Monte Carlo. But still, this system is difficult to handle because you see here there is a complex value part which makes the integration very difficult by doing the Monte Carlo simulation. Namely, the system contains the sign problem of the Monte Carlo simulation. There are some ways to deal with the sign problem in Monte Carlo, but here in this talk, we just apply the most naive method, which is called reweighting method. The idea of a reweighting method is very simple. Just split the system into two parts. One is the one with the real part, and the other with a complex part. And the real part defines the system, and now the complex part can be computed by the expectation value defined in the system defined by this real part. Now here I show you the product of airy functions. The reason why it comes is that I have already done this five-children integration. This is nothing but the integral representation of the airy function. So I just rewrote it by airy functions here. And what is important in this expression is the negative sign of the argument of the airy function. In this negative region, airy function has this oscillatory behavior. I will explain later a little bit more, but in the quantum phase, the phi square fluctuates very widely. This means that the computation of the expectation value is a sort of contains many cancellations because of the oscillatory property of the Airy function. Therefore, I will explain later more, but this factor, the expectation value, suppresses the appearance of the quantum phase. In other words, this expectation value highlights the classical phase. So physically, this part is very important for our physics. Now let me show you the presence of the two phases in the system defined by this real part. So now let me assume Q to take Lie group invariant value. What I mean here is that the tensor Q is invariant under certain representation of a Lie group Z. When lambda is small, this is in the quantum phase. What I mean is that the fluctuation of phi square forms the one bunch like that, and the fluctuation width is large. When lambda becomes larger and larger, the bunch splits into two, and the fluctuation becomes small on each bunch. This is called the classical phase. So there are two phases, and the two phases are characterized by the topology of the distribution of the phi square. And it has a similarity with a transition between one-cut and two-cut solution in matrix model or Gross-Witten-Wardier type transition. So now here comes the actual data, and here I assume the SO2 invariant tensor Q, and the results are more or less similar for SO3 and SO4. And let me look at the data here. So the distribution of phi square is like that for lambda equal 10 to 3, but including the lambda, the distribution is deformed, and eventually it splits into two parts. And from now, I want to call the bunch which is near to the origin, center bunch, and the other outer bunch. Now here I'm showing the actual Monte Carlo sequence, and this is the sequence in the quantum phase. And as I show here, the phi square fluctuates in a wide region like that. In the classical phase, phi squares are concentrating around each bunch. But sometimes there is a transition of phi's from one bunch to the other. But what is curious here is that if there is a transition like that, then there is always a transition in the opposite direction. This is illustrated here. So as a net effect, there is no change of the values. I mean, this is just the rename of the phi's, but there are no change of the values as a Monte Carlo sequence. So from this observation, what we can say is that the set, the inner products and cell products in the outer bunch is the semi-classical or the parameter for the classical phase. And so these values determine the distances between the phi's. So therefore, in other words, the set characterizes the semi-classical geometric structure of the outer bunch. So now I'd like to discuss first the topology of this outer bunch. So what I want to do is just connect the nearest neighbor phi's by lines. If you do that for SO2 symmetric Q, then what we can find is S1. If you do that for Q equal SO3 invariant Q, then what you find is S2. And you can do this for SO4, and the conclusion is that the outer bunch is topologically Sn. Now, how about the geometry? We can discuss geometry by checking the Laplacian. I cannot go into the details here, but I just want to tell you that we compute the spectra of the eigenvalues of a matrix, which is given by this form in the outer from the phi's in the outer bunch. Then what we find is that the spectra which is consistent with the Laplacian on Sn. These are the results of the spectra, the eigenvalues of this object, and this looks similar to the Laplacian on Sn. Now let me explain how to construct the SOn+1 invariant tensor Q. So this is done by preparing the eigenfunctions of the Laplacian, and we consider products of three of these functions and integrate them over Sn. Then we can construct SOn+1 invariant tensor. The preparation of the eigenfunctions are given like that for each case of the SOn. And basically, the idea is to take from zero mode to a mode of a certain momentum labeled by lambda. This is a physically natural choice because then this lambda can be interpreted as an ultraviolet cutoff. But of course, we do not have to follow this way of constructing the SOn+1 invariant Q. What we want to discuss from now is to break the legal symmetry and change the set of representations. I mean that you may be able to add something to Q to break the SOn+1 invariance. And here we took the eigenfunction from zero momentum to some momentum, but successfully, but we may drop some of them. But anyway, what we can find is that such deformations tend to turn the classical phase to the quantum. And as I told you, this expectation value suppresses the amplitude in the quantum phase. Therefore, this part suppresses the deformations. Now let me show you the actual data for breaking Lie group symmetry. And this is now I consider the SO2 symmetric Q here, but add the SO2 breaking tensor Q. I do not explicitly write how we broke it, but it's one tensor which breaks SO2. And what we can observe here is that if you break that, then the expectation value drops quite quickly. And also, as for the phases, if you when z equals 0, invariant case, the system is in the classical phase. But if you add z, then it turns to a quantum phase. This is the case of different choices of the representation, again, for SO2 invariant case. And omitting zero mode is fine, but omitting zero mode and the momentum one mode make the system in the quantum phase. Now let me discuss the general behavior of the wave function under the change of the size of the tensor Q. To do that, let me introduce a new variable, Q tilde.
You have 5 minutes.
Okay, thank you. This is the last section, so I will end it very quickly. And so Q tilde is a sort of angular part of the tensor Q. And by doing rescaling of the variable, you can derive this expression here. The difference is that the coupling is effectively given by lambda Q squared. So this means that as Q becomes larger, the transition from quantum to classical occurs if there is a transition for this of such a Q tilde. Another effect is that because of the size dependence of the argument of the area function, when Q becomes larger, the suppression by the area function becomes stronger because this dependence enhances the cancellation of the expectation values. So the speculation about the history of the universe in the canonical tensor model looks like that. When the Q equals 0 and the size is equal 0, then the system is in all quantum. But eventually, when the size becomes large, only the classical the wave function remains only in the classical locations. This is my summary, and there are two phases. And in the classical phase, there emerge classical geometric objects, and the area function part, the expected value part, is very important. And this is a future problem. There are a lot of problems which I have to solve, and maybe the first question would be how to remove this extra parameter lambda. And because of the from the physical point of view, it would be interesting to discuss whether the spacetime in CTM is glass or not because of the similarity to the spin glass model. And of course, as a physicist, I want to do some computation which can be compared with observations. And there are other problems as well. Okay, thank you very much for listening.
Okay, let me first see if there are questions from the local audience. And
the laptop mic, is it on?
Yes. Okay, now, yes, George, then I have a question, actually.
Yeah, hello, here is George Panos. It's very interesting what you do. We have done similar things in the classical level using the Lie structures. Maybe you know our papers. An interesting thing which we would like to do in the future is to consider cosmology. And from your last slides, I see that you have this kind of problem in mind. So the question is, do you have a feeling how far one can go in studying cosmology?
Yeah, that's a really interesting question. Yeah. Currently, I feel very distant, but as you might, as you know, the things may change very quickly by some, some discoveries, and so in the Sylvie. So I hope that I can, I do not, turn down the possibility that I can say something in cosmology at the next conference in Corfu. Yeah.
Okay. I actually have a question.
Okay.
It's about the role of the constants, the scales, more correctly. So you consider this lambda, a small lambda, as a smearing, but now we know that probably there should be some physical smearing. So is it possible to give some sort of physical meaning? Because in any case, you have a scale, which is this Q, which is more dynamical, and we know in the there will be at least 3 scales. One, you say equal to 1 because you are in space-time. So is this lambda just a device, or can hide some physics behind it? That is the question.
That is a really interesting question. And I thought about this possibility as well, because of course the observation cannot be, precisely. So anyway, any observation would contain some ambiguities, and maybe if I identify something, for example, some matter field or some observable apparatus, if I can include them into this canonical tensor model, then I suppose that this kind of smearing parameter appears very naturally in some way. Yeah, of course, I'm not so sure yet, but I believe so. Yeah.
Yes. I'm sure that if you knew, you would have told us already. But,
no, I don't know.
Sorry, because I'm sitting. There is no, I don't think there is other question. Let me see on the chat. There are no more questions, and we are in fact on time. And we thank again Naoki Sasakura.
Thank you very much.
And we go now live. The next speaker is Walter van Suijlekom, and let me see. Okay, the title is there. Cyclic cocycles in the spectral action and one loop corrections. And I will give you the usual warning after 20 minutes, so that you have 5 minutes to finish, and then there will be about 5 minutes of questions and answers. Please.
Okay, so thank you. Thanks for the invitation. Pleasure to give this talk. So let's get to business because time is short. So let me first explain what type of approach I would take, and actually other speakers this morning, to non-commutative spaces. Is it on? Should be on. Okay, so this is the idea. So we take a spectral approach to non-commutative space in geometry, and then in a generalized sense. And this is also referred to non-commutative geometry à la Con, or non-commutative differential geometry. But the basic idea is that we take a spectral approach. And with spectral, I have a couple of, it's like a package, a spectral triple, where I take a star algebra, which acts on a Hilbert space. And there is this self-adjoint operator D around with some properties, also acting on that same Hilbert space. But the main point of this, if you're not familiar with it, and in fact the talk will not rely too much on it, is that I have some coordinate algebra, A. I have a D, which is like a Dirac operator, which I tend to think of as an inverse fermion propagator, which is essentially the same thing. And this Hilbert space is a one-particle space of fermions. So there's just single particle, no Fock space, it's just one-particle fermionic space. The idea of this approach is that with this package, under suitable conditions, you can actually, so in the case that A is commutative, is a commutative algebra, you can reconstruct a Riemannian spin manifold from this data. And that's really the point which is central in this approach, is that you kind of capture ordinary geometry, but then generalize it by allowing your algebra to be non-commutative. So that's say the setting, the formalism. And the interest in physics is the following, is that actually given such a package, such a spectral triple, you can do gauge theory quite naturally. So the first thing you get is a gauge group, which are the unitaries in the algebra. And they act by conjugation on this D, and what you find, as usual actually, this is very common in the physics derivation, you get a pure gauge field that you add to the Dirac operator. They couple it minimally. So then, okay, the next question is, what kind of invariants can you construct? So can you give something like an invariant functional, an action functional? And that again is based on a spectral idea, is that you look at the spectrum only. So it's a spectral invariant. And the best, actually essentially the most general thing you can write down is the trace of f of d, where f is a suitable function that makes this, this operator f of d traceless. So, and this is actually where also there's a similarity with the functional renormalization group, where you found, where you could see this term at the right-hand side, maybe with f written as w, and d is replaced by the Laplacian or the inverse Laplacian, but essentially it's the same idea. And the point here, though, is that this gives us a classical starting point. It gives me the classical action functional, and actually this talk is about how to improve on that. And so then, well, okay, pure gauge fields, that's not very interesting maybe, so let's try to find more general gauge fields. And with that I intend inner perturbations, where you again use the data that you're given to construct perturbations of D, which is this D prime over there, which is a term which is linear, and it involves elements in the algebra. And you should think about them as one forms, so differential one forms, where the commutator with D is like the differential. So these terms are what I would call gauge fields. And so actually this works in a good sense, because you can do actual physics with it. And what you may do is to apply an asymptotic expansion. So the same techniques as with the functional renormalization group equation, is that you can apply like heat kernel. So there's suitable conditions on F in this case, of course, but there's like heat kernel methods that you can apply to find an expansion in powers of the cutoff lambda, this cutoff parameter lambda. F is still, I mean, it should be something like an exponential, or at least something related to that. And the alpha k are these local expressions which are gauge invariant, but also geometric invariants. And in particular, and this was actually already mentioned in the first kind of contribution by Harold Grosse, attributed to Mador, which is very similar, is that if you take like matrix coordinates, so it's like matrix valued coordinates on an ordinary space-time manifold. So these are called almost commutative manifolds. So the package would be to have something like okay, you have like functions on M with values in this matrix algebra. You also have this inner space of spinors, which is this one. So you extend the space with this HF, which is a finite dimensional Hilbert space. And then there's also this coupling of the Dirac operator on M with a Dirac operator on this finite space, whatever that may mean. So that's in this case just the Hermitian matrix. And then you find the expansion to be as follows. And the first thing you find is actually, well, the volume, but you also find Einstein-Hilbert Lagrangian. And there is also this R squared contributions that are also found in the FRG approach, because the same methods are applied. So it's actually nice to think about renormalization or renormalizability of such an action functional, because you get these terms in there that you would like. And the other terms are Young-Mills for this case. And then, and that's actually good motivation, there's the Higgs mechanism that you kind of derive, in the sense that you get a minus sign in front of the square. So I'd love to talk about this more, but time is short, as I said already. So I want to talk about something else, but this is just to motivate where the spectral action has something to do with physics. But as I said, it's classical, and we want to kind of improve on it. So what I would like to do is to understand the another expansion of this action functional, but now in powers of this perturbation V. So V, that's this this commutator of D with Bj. So this is the gauge field that you add to it. And what I would like to understand is how you can expand this in powers of V as a perturbative series. Now, actually, it is shown in several forms. So first of all, I did it myself under some conditions on F. This was then improved by Skripka with less conditions on F or different conditions on F. Then Teun van Nuland, which is my PhD student, with Anna Skripka, they again improved on it. And then more recently, we also gave an alternative. It's about kind of the balancing the conditions on F and the conditions on D. That's what you play with. And this has very much to do with spectral flow, etc. And so in any case, the point is that this is the formula which is kind of most suitable for this audience, because it's this bracket that you find over there. When you plug in these different gauge fields, it's a trace of a contour integral of the derivative of F, and the contour is taken over the spectrum of D. And what is nice about this is that you can represent it as a diagram, which is quite familiar because I take a trace. When I consider these V1s as external gauge fields, in between there's just the propagator of the fermion, so I can draw it as such a fermionic loop diagram. That's quite a convenient way to think about it because that's essentially what it is. Loops corresponds to the trace. So these are the terms that you find in the perturbative expansion of the spectral action. So these are the ones. Let's analyze their structure. So the first thing is that there is a cyclic permutation symmetry. So of course I have a trace, so it doesn't really matter if I change the order in a cyclically commuted manner. But there's this second ingredient, the second condition, property, sorry. Not a condition, you can just prove it. Where you multiply first with A, V1, and you do it, say, after the comma, or so Vn times A. This you can do, you can interchange the two at the cost of adding a derivative of A. So it's this extra term. So you get one more term. And this is actually also something which is quite familiar if you think about what it means. Namely, this is actually it boils down to this equation, which you can just show by staring at it for a while, which you can multiply by Z minus D on both sides, and you just find it modulo all kinds of domain issues, which I won't talk about. But this is the way to depict it. It's like you have this fermion propagator, and then you insert A, or you first insert A and then fermion propagate. This is just giving me an extra vertex contribution. And in physics, this is a what identity. It's like you put in momenta before and after the propagation at the cost of adding a vertex contribution with the derivative. And that's exactly the same. I mean, if you know how to derive the what identity in QED, it's the same formula that I applied here. The same technique. So, and this is something to keep in mind because these are the only two properties that I will use of this bracket. And everything, all the derivations, all the results rely on these two properties, 1 and 2. So the cyclic permutation and this kind of what identity. Okay, so let's see what we can derive from that. So what I would like to do is to get to some integral formulas. Just as before, I had these integrals over the manifold of curvature and so on. I would like to see if I can do this in this general sense. And for that, I will use integrals, non-commutative integrals over universal differential forms. And this was already mentioned in, say, 2 days ago by Joachim's talk. And if you would like a good reference, this is also the place to refer to the book of John Mador, where this is carefully explained. These universal differential forms, well, of course, also in other books, but in particular in John Mador's book, they're like the most general thing you can do with forms where you don't impose relations on the derivative, the delta, in this case, of elements in the algebra. And what you can do with it is that if you have a multilinear functional on A, so it takes values A0, AN, such that if one of these A1 up to AN, if it's scalar, then you get 0, then you can actually write it as follows. You can write it in terms of an integral. I mean, it's just a symbol with phi n, which is defined on the differential forms. So it's sufficient to know the differential form to be able to express this linear multilinear functional on A. And this is the type of kind of symbols that I will use. These non-commutative integrals are understood in this way. It's not like integrating anything, it's just a multilinear functional applied to these elements. And in particular, we will be interested in this one. So what I will do is I take this bracket that I just introduced, or maybe this one, whatever, it's the same thing. So you look at this and you insert A0, DA1 at the first slot, DA2 at the second, etc. And this I will call a phi n, and that's a different phi. So that's the one I will use in the following, but this is the general definition. So I will use these non-commutative integrals, phi n, and I would like to understand how my series, my brackets that I find in the perturbative expansion are expressible in terms of these integrals. Okay, so let's see what we can do. I'll just give you a few examples. So the first one is for one external edge. So I get just one bracket, V inside, and V is this combination, and A is the universal form that corresponds to it. So it's AJ delta BJ. Now here you see that what does this bracket mean? It's just this loop diagram, just a tadpole, and it's already in the form of what I called phi n. So this is the integral of A with phi 1. Okay, that's not very interesting. Maybe let's look at the second one. Two external edges. Then you find that you have to get a bracket of two V's, which means that you have first this AJ dBj, that's the first V, and then you have the second V, which is multiplying AJ prime, that's what this means, this dashed line, with dBj prime. But then I can apply this word identity. To move it, say, along the propagator, you move it backwards, you get it over there. So it's multiplied here, at the cost of adding another vertex. So that's the only rule I'm applying here, where you see that now this one here, this you can rewrite in terms of A squared, is the integral with respect to phi 2. And here I generated another vertex, which means I have a higher order in the differential forms. So I have this delta of AJ prime, which you can translate in terms of the A, capital A, as the integral along phi 3 of A delta A. And the only rule, again, is this number 2 in this case. Then this continues. You can just do the combinatorics. Essentially, it's just, it's not, well, of course, the challenge is to write this in general, but here are the few cases that you can find. And okay, so you have the first line, it's rather neat, but then there's all these terms, and this goes on. So it's not completely clear what this is, if it's anything at all. So let's try to organize this a little bit better. And what I will do, I will shift my phi to a psi functional, which is just the difference with the total boundary. So it's essentially not so important, even though, I mean, it's not 0 or something. It's just that there's a delta O, a total boundary that you add to it with respect to phi 2k. And then what you find is that if I combine the two terms that I just showed you on the previous slide, which is A and A squared, then if I replace phi 1 with psi 1, I get the integral over A, plus I get this additional term, which is delta of A. So this is the integral of, well, there's also this A squared, and the 1/2 really adds up to get you delta A plus A squared. So that's already nice. But it's even better when you continue, because then you add the additional contributions again from the previous slide. Then if you make the transition from phi 3 to substitute psi 3, then you find that you have this term A delta A, then there is this additional term 2/3 A to the third, and then there's 1/4 delta A plus A squared squared. And now if you, I mean, if you look at it, you should be able to recognize what this is, what we're getting at, because maybe this one is most clear. This is a Chern-Simons term, and this is the curvature squared. Whereas here we had the curvature, which is delta A plus A squared at the universal level, and here we have actually a Chern-Simons term of order 1. Now this continues. I mean, that's a lot of work, of course, but you can actually do it. So under suitable assumptions on F, you can, using only the properties 1 and 2. So that's really something. It's just the basic 2 properties that I use of the bracket. I find that I can expand the perturbative expansion in V in terms of Chern-Simons forms and curvatures to the power k, so higher order Yang-Mills terms. And these Chern-Simons, they also appeared already 2 days ago on this meeting. They're defined as usual by just by applying this digression formula or this integral, and indeed you get the usual order 5 Chern-Simons, etc. So that's something which is really kind of, there's nothing else but these 2 terms, Chern-Simons and Yang-Mills, 2 higher powers. Now the point is, these psi's and phi, they have a very nice property, and also my title was Cyclic cocycles, but this I will not tell this week. But in about 1 week from now, there will be a meeting which is online at the Fields Institute. You can still try to find it if you wish to learn more about cyclic cohomology, because they turn out to be cyclic cocycles, both of them. So one is odd and the other one is even. So they also have a meaning in a mathematical framework, which is, just to summarize, cyclic cohomology would be the replacement of the Ram cohomology, actually the Ram homology for the manifold that is underlying this. So in the classical case. Okay. So why I don't want to talk about this now is that I want to talk about the loop corrections. Let's see what we can do, because this is still a classical perturbative expansion of my classical action functional. So with that, I mean the following. So I will apply a background field method. So this means that I will take some background field and only fluctuate around that. So let me actually spell it out. So my V, that's my gauge field, the one I started with. That will be my background field. I just keep it as before as kind of an external. These V1s are just external fields. But I fluctuate around it with a Q, and that's a quantum field over which I will do a path integration. And this I allow to be an arbitrary Hermitian matrix of a finite size, n, which I consider to be a regulator, so that I can actually do this path integral, which then I try to set to infinity later on. And matrix, I mean, in an eigenbasis of D. So the given D that I started with, the Dirac operator. So Q is allowed to be more general than just elements of this type. And in fact, if you write out what these brackets mean, because they should tell me what the propagator is, what these brackets mean in terms of the Q. So then the quadratic and the cubic terms, but this propagates to the quartic, etc., to all the terms, they are just like a matrix model with some interaction terms, some dynamics, which is given to me as in the form of a divided difference, which is written like this, like a finite derivative of divided difference of Newton, which is defined down here. But you find that this is the one at second order, and at the cubic level you get the one of order 3, and this just propagates. You get the same formulas, but just extending these formulas to arbitrary order. So what my task is to understand if I can invert this divided difference of order 2. So I have a propagator, and then these other things are the vertices. If you take a suitable f or f prime, well, suitable f, you may perform the Gaussian integration by just by doing the integral. So there's no need for gauge fixing, because I'm in the situation where I can do the Gaussian integration directly, like with matrix models actually. And it's just 1 over f prime lambda k lambda l, of course. And this is an example of a bump function for which that actually works, for which you can do that. And this is the divided difference, so it's positive and never 0. So you can so you can try to analyze kind of vertex contributions, and this is what I will do. And in fact, what you can do is you can try to look at all 1-pi diagrams that you build from these propagators. Yeah, thanks. Very good. And I will call them double brackets. Okay, so they're just the sums of diagrams that you can make, where I now not only have these fermion vertices, but I also have internal propagators of this type corresponding to the Q, actually. Then, crucial property is that there is a bosonic wide identity as well. So we have the one for the fermions along the fermion propagator, but actually there's another one, which means that along a bosonic propagator, if I insert an A before or after, it's at the cost of adding another vertex. So you have exactly the same kind of reasoning as before, but now you have this additional term. And this all happens inside the diagram. So it's the internal propagators for the gauge field, because the external ones are like with 1pi diagrams, they're not propagated. Actually, this formula, it induces number 2 prime, I call it, for the one loop. I mean, that's the status of the project. So at one loop, you look at the divergent part, then that will actually satisfy the same equations that I had before. So you first multiply with A, you compare it to what you did when you multiplied with one before, it's at the cost of this D commutator A. Now, cyclic permutations, I mean, that's clear from writing it this way, because I look at all the diagrams with these kind of, these things as external lines. So this means that I have cyclic permutations by definition. So this means I have 1 and 2 also for these one loop contributions if I restrict myself to the divergent contribution. Let me give one example and then I get to the final slide. Is that, let me sketch diagrammatically how you prove such a thing. So by looking at these diagrams at one loop order, so I should say one loop in the gauge fields. These are considered to be vertices, these fermion loops, but it's with 2 external lines, and these are the 3 points. Now the first thing you realize is that this one that kind of crosses, it's like with ribbon graphs. If you have such a crossing, it brings one index which is external to the inside, so it does not propagate anymore. So this means that this one is actually finite. There's no sum involved at all. But this one here inside there's an index running, and that's actually potentially divergent. So if I look at only those diagrams which have that property, then I get the following, and this is just following the diagrammatics. I find this for this diagram in the middle here. So I first insert A and then look at what happens after inserting A, like this. Then you get these contributions by applying these Ward identities, both for the fermion propagator and for the gauge propagator. And well, since time is short, I will just say that, well, this is the other diagram, this one, the third one in that table, for 2 external lines. And of course, you can assign V1 and V2 in 2 different manners. So there's 2 of them. But if you take all of these into account, and as usual, by checking this, the right-hand side forces you to rethink what you put on the left-hand side, whether you forgot the diagram or not. So this is the usual thing with Feynman diagrams. And then you find with all the topologies that you can think of, which are divergent, you get to need the full package that you need for the right-hand side. So this means that with such reasoning, you can show that this equation holds, and this just continues to hold more generally for arbitrary endpoint functions. So what this means, this is the final statement, is that what happens is that these one loop contributions, if you restrict to the divergent part, they satisfy this 1 and 2 prime. But it means I could start my talk again. I won't do that, don't worry. But with these 2 properties, I derived that it was Chern-Simons and Young-Mills. So this means that also for this, I can do that same derivation. So these one loop divergent contributions to the spectral action, they have the same properties, so they are of the same form, with different psi's and phi's now, which are defined in terms of the double brackets. But it means that I can absorb these divergencies into the spectral action I started with, and get a sort of a one loop renormalized spectral action by absorbing this into the cyclic cocycles along which I integrate. So you get like this step by changing the kind of the integrals, the non-commutative integrals, but keeping the same form, you get this renormalizability at one loop. And this is of course a very nice feature, because everything now on the right hand side is spectral. So I kind of stay within the same framework and still can say something about one loop renormalizability. And that's my final word, so thank you.
Are there questions?
Yeah. Thank you. In principle, can you repeat this algorithm to go to more than one loop correction, or the method is really just for one loop correction?
Yeah, so of course that's the next step. So it's clear that this is just the beginning. And now one has to find the systematics, but maybe you remember Grosse Wolkenaar, how this started. I mean, it was to get to ribbon graphs at higher loops, one really has to kind of develop some more mature framework. But this is a work in progress. So, yeah, a good point.
I had to go out, so I missed the first question. First of all, I find very impressive what you did, and I'm sure that you can check with experts that is correct and so on. Actually, it was a debate between me and Fidel a few years ago. Both we knew that all this story was classical, right?
Mm-hmm.
So only of prejudices, Fidel was thinking that it's normalizable, and I had some doubts. So I'm very happy that it's a very huge step forward. What about gravity?
You want another? You want another huge step? Yeah, exactly. No, so I didn't. So this is really the gauge sector. So you're completely right, of course, in asking about that. And so for that, I have now nothing within this context to say. I mean, it's because they don't. Well, it's interesting to think about it because, I mean, the perturbations I look at, they're like linear perturbations. But of course, if you want to kind of change, kind of make gravity more dynamical, you have to do something more stronger than that. I mean, you have to change D in a nonlinear fashion, not just non-affine fashion. I mean, it's just so it's that's I don't know if you will say something about this, Andrej, but there's or maybe Pierre, but there are several kind of attempts in that direction, but not within this framework yet. But yeah, right.
Oh. I have a question, and this V can be any operator. Doesn't have to be. While when we do Feynman diagrams, we are perturbing the free propagator, which would be D, with a potential which is a function of X. But here, your V can be any operator because everything is spectral.
Yeah.
So in principle, you can see perturbing D with D itself, which you know the answer will be just a multiplicative factor, but this can give you a hint for higher loops. So it's like when you do in class, I often do the harmonic oscillator, then I add a perturbation, which is X squared. So of course, I'm just changing the constant of the harmonic oscillator, but it's very instructive because you can see how in fact, you can sum the perturbative series. And here probably you can do something similar because you can perturb with differential operators.
That's right. Yeah.
Which will be very difficult in ordinary field theory.
Yeah, so if you stick with first order, I don't know if that's what you intend, or do you want to, because you could also think about fluctuating D with a quantum fluctuation for the fermion propagator.
Yes.
But that would be not first order. Now, I did have some experience in not first order perturbations, so it could be that could be helpful. But at one loop, so at the first order, I don't know if.
Okay, just
good point.
Gaetano, another question.
One standard way to derive the renormalizability of Young-Mills theory is through BRST quantization and BRST formalism. So you can derive word identities using BRST. Can you see a connection between your approach and a BRST transformation?
Yeah, so it's a very good point. So usually, of course, you have a BRST formalism, or even in this case, you would need a BV formalism because of the fact that that these matrices ask for such a more general formalism. However, like with matrix models, you can kind of choose. So if you read these older first papers on matrix models, where you either can do this Gaussian integration, and you get propagators, and you can actually try to solve it like that. But what you could also do is to integrate, instead of over Q, over all matrices, you integrate over some diagonal matrices and unitaries, because you can diagonalize all of these Hermitian Qs, of course. And that's precisely where you find kind of reminiscence of a BRST formalism, because then what you're doing, you change the measure to diagonal matrices, which might be easier to integrate, of course, and to see what this means, because then this would be much easier to solve. But then this unitary transformation, it tells you that that there's a volume that you have to take into account, and that's just like this van der Monde determinant if you compute it. That will be kind of the transfer of the Jacobian actually to the other volume integration, volume form. That would be the Jacobian for that. That would mean this determinant that you can understand in terms of ghost fields a la BRST, which is very elegant because you can see it happening, but by just changing the measure, and it's all well defined. So for now, I tend to. It's a good point. So in fact, if you want to do the integration not over all of these matrices, but stay within a smaller class, then this is absolutely important to do a BV kind of approach. So I agree, but I cannot say too much at this point. I don't know. So.
Okay, I don't see questions in the chat, and we are running slightly late, so we thank again Walter for the talk.
Thanks.
And the next speaker is Pierre Martinetti, and the title is Standard Model in Non-Commutative Geometric Rotations and Twisted Spectral Triples. Okay, and as usual, I will. Yeah, oh my God.
So just let me start. I just realized I forgot in my affiliation to add actually the one who are funding my visit here. So I'm just writing here. I just wrote the University of Genova, but I must also quote the Istituto Nazionale di Fisica Nucleare. Okay, so this work, I mean, I would like to present various results obtained with several people. So there is Devashish Singh. Where is the light here? Where's the light? This one?
Forward, backward, and
okay. So Devashish Singh, who made his PhD in Genova, but he has now left academia. There is Jacopo Zanchetin, who is actually a PhD student in Trieste at CISA, and Manuele Filacci, who is actually finishing a postdoc in Genova. So Walter has already talked about that, but let me recall you that so starting from the pioneering work of Dubois-Viollet, Kerner, and John Mador, we made the observation that the Higgs field can be obtained as a kind of connection in some matrix model. Then this has been later incorporated in a more global framework by Kohn into his framework of non-commutative geometry. And so this led to a description of the standard model of fundamental interaction together with the Einstein-Hilbert action of general relativity through the spectral action that Walter has already talked about, and I will give more details on how to apply the spectral action precisely to the standard model. Actually, it goes a little bit already beyond the usual standard model because it includes right-handed neutrinos. And of course, as Walter had said, there is also this idea that the Higgs boson come out naturally in this framework, and this was, I think, really the original idea of this paper of Mador, Kerner, and Dubois-Viollet. The Higgs boson comes out naturally as the other gauge boson, that is as a connection one form, as a local form of a connection, but a connection which has to live in some non-commutative part of space-time. So all this framework of non-commutative geometry works very well in Riemannian manifold. This is what Walter has said. From the spectral data, you can rebuild a Riemannian manifold, but it is well known that the generalization of this approach to Lorentzian manifold is far from obvious. There are various attempts, but so far nothing has really emerged as a non-commutative Lorentzian manifold. So what I would like to talk here is that by non-commutative geometry also offers some kind of toolkit to go beyond the standard model, applying all this technique of spectral triple. We can go beyond the standard model, and here I've listed several approaches, so I will not give the details. Basically, you play with the rule of the game with the mathematics, and you can go a little bit beyond the standard model. And in all this approach, except the first one, where it was more radical because you were adding new fermions to the standard model. In all these other approaches, I will call them some minimal extension of the standard model, in that the fermionic content of the standard model is not touched, it's always the same, but you add new boson. And why do you add new boson? Because actually there are some problems in the standard model. I mean, some particle physicists suggest that there is some a problem because there is an instability of the vacuum for the Wick interaction. And a way to stabilize this instability is to assume that there is extra scalar field beside the Higgs. And in all these ways to go beyond the standard model in non-commutative geometry, you manage to give this new extra scalar field. And the one I would like to advertise is the one we started with Fedele Lizzi and Agostino Devastato in Naples, then we moved forward with Gianni Landis and with people in Genova that I've quoted at the beginning, especially Emanuele Filacci. And by using which is called a twisted version of non-commutative geometry, so it's something I will explain in more details, which has been introduced by Kohn himself, but not at all related to physics, just for purely mathematical reason. But then it comes out that it has nice application, so in the physics. And by doing this, not only we find this extra scalar field, but there is a new pieces that was completely unexpected. And this new pieces, we had some trouble to understand what it is, but it seems to indicate a possibility to make a transition from the Euclidean signature to the Lorentzian signature. So this is why in the title I put Wick rotation. Actually, it's not really the Wick rotation. It's just a short word to say transition from one signature Euclidean to the Lorentzian one. So let me recall you fastly what Walter has already said. So a spectral triple is an algebra which acts on Hilbert space together with a self-adjoint operator D, which satisfies some property. Here's a property what are important for us is that the commutator of this Dirac operator with the algebra should be bounded. There is also a grading, so we call the graded spectral triple if there exists a graduation of the Hilbert space, so an operator which square to 1, which is self-adjoint and which satisfies this property with the algebra and with the Dirac operator. And there is also a notion of real spectral triple in which you require one more operator, this operator J, which satisfies this property. So I will not give the detail of that. The fact that all these objects should also satisfy two conditions, and one that will be important in this one, which is called the first order condition, which is an algebraic way to state that this operator D that you are starting here, that you are taking here, is should be a first order differential operator. So this condition is an algebraic way to characterize a first order differential operator. So we will use this condition, and for the standard model, so what is this spectral triple? Actually, it is a product of a four-dimensional Riemannian closed spin manifold with a finite dimensional spectral triple. So here you've got the total spectral triple. So C infinity of M are the smooth function of this Riemannian manifold, which act by multiplication on the space of square integrable spinors. And there is the usual Dirac operator D slash. And then you make the product in the sense of spectral triple with a finite dimensional spectral triple, which is given here. So the algebra is a complex plus the quaternion plus the 3×3 matrices. So why this algebra? There have been many papers to explain this, so I will not give the details. It acts on C to the 32 because here I work just with one generation of fermion, but the model can be extended to 3 generations. And in one generation of fermion, you've got 32 particles. So as Walter said, this Hilbert space here is the space of fermions. This operator is a generalization, let's say, of the Dirac operator. And so on the finite part of the Hilbert space, you've got an operator that acts, so a 32×32 matrix. And here you put the parameters of the model, which are basically the masses of the fermions. There is also the Cabibbo matrix. And the matrix for a few generations, there is also the matrix mixing for the neutrinos. So you put all these parameters in this matrix. In some specific places in this matrix. And what is important for us that this matrix, so the DF, the finite part of the Dirac operator, you can divide it into two pieces. There is a diagonal part and the off-diagonal part. And the important thing is that in the off-diagonal part, you just have one entry, which is the Majorana mass of the neutrino, because we assume there is a right-handed neutrino. So we've got the Majorana mass for the neutrino. And this is the only one which enters into this off-diagonal part. All the other parameters are in the diagonal part. Okay, this comes from the condition of non-commutative geometry of spectral triple. So this is how the model works. I will not explain why, but at the end, after many works, this is where one arrives. So Walter has also explained, here we just have the fermion. If we want the boson, we have to make what is called the fluctuation of the matrix. So we'll replace the operator, the Dirac operator, with the covariant operator, which is given by this formula here, where A is a generalized, is a connection in the framework of non-commutative geometry. So we've already made this formula in Walter talks. It is an element, a self-adjoint element of the generalized one forms, which are here. And if we do that just for the standard model, so you apply this formula for the spectral triple I have introduced for the standard model, and this is here where you already see that the Higgs boson come out exactly as the other gauge boson, okay? Because if you compute this formula for this spectral triple, you will see that it divided in two pieces. One, which is one form field with value in the Lie algebra of the unitary of your finite dimensional algebra, so the complex plus the quaternion plus the 3x matrices. And this is exactly the mathematical definition of a gauge field, okay? And so the gauge group of your model will be the unitary of this algebra, and this will give you the U1, U2, SU2, SU3 of the standard model. And there is another pieces, which is a scalar field on the manifold, which has value in this in the finite dimensional algebra, and this will give you exactly the Higgs field. Okay, so this is really from this formula that we see this idea that the Higgs is a component of a connection, but a connection which lives in the non-commutative part of the geometry. And as Walter has explained, if you take the trace of the square of this operator divided by a certain scale, and you take the asymptotic expansion of this, then this is the spectral action, and this will give you, for this particular spectral triple, this will give you the Lagrangian of the standard model, plus the Einstein-Hilbert action, plus the Y term, plus a minimal coupling between the Higgs and the curvature. But of course, everything is in the Euclidean signature. So this is the Einstein-Hilbert action in the Euclidean signature. So now, how can we go beyond the standard model? As I said, there is this problem. Some will say it is not a problem, but that's another debate in particle physics. The fact that the vacuum of the electroweak, the electroweak vacuum is not a stable state, but it is a metastable state, and so there could be a possibility that it goes by tunneling effect to its very lower level, which is minus infinity, and destroy the whole universe. So there are various models which explain that. And so an idea to cure this instability is to assume that there is a new scalar field, okay? And in non-commutative geometry, this has been noted by Kohn and Shamseddin just after the discovery of the Higgs field, that if as I told you, there is this parameter here, which is the Majorana mass of the neutrino here, which is a constant. If you turn this constant into a field, so which is written here, this kappa r, now you make it a field, then you compute the spectral action before, then this gives you exactly the kind of field you want to solve this problem of the vacuum of the electroweak interaction. And it also has another advantage that in non-commutative geometry, you can compute the mass of the Higgs because it is it depends on the parameters of the model. And if you compute the mass of the Higgs, there was a prediction before the discovery of the Higgs field, and it was too heavy. It was around 170 GeV. But if you put one new field, then you've got a new parameter, and you can fit, let's say, naturally this new parameter, so that to compute the right mass of the Higgs. So this way of turning one constant into a field has two advantages. One, from purely particle physicist point of view, it gives you this kind of field that maybe are used for the standard model, and just inside our framework of non-commutative geometry, it allows us to solve the problem that the computation of the mass of the Higgs was not the correct one. Okay. So the problem is that how do you justify that a constant become a field? And the point that actually, if you look a little bit more into the details of the model, we have put the constant in the model, and we generate the gauge field by this fluctuation of the metric. And the fluctuation of the metric basically consists in computing the commutator of the operator with the algebra. And the fact that why this constant doesn't give the field if you make this fluctuation of the metric, because the part of the Dirac operator where it belongs to commute with the algebra. So it is natural that it does not give you a field. So here it seems a bit artificial to say, okay, we've got a framework to turn constant into a field, but there is one constant because it is located in the Dirac operator in a peculiar place, so it cannot become a field. But still, we would like it to become a field. So how can you justify this? Because we should not contradict our own rule. So there has been various attempts to justify this, and the one I would like to explain. So this is this idea of twisted spectral triple. So here the idea is to say instead of if you look at the framework of non-commutative geometry, at many places there is a commutator of the Dirac operator with an element of the algebra. I mean, it plays a crucial role in various places. And what Kohn and Moscovici have introduced in 2008 is a twisted version when they say, well, okay, instead of considering the commutator of D with the algebra, we can take a twisted commutator. So the formula is here. So you see it lacks a commutator, except that when you write the negative term, you act with an automorphism of the algebra. So you fix from the beginning an automorphism of the algebra, and you define the twisted commutator in this way. So why do you do this? You could say it's totally artificial to make this. Actually, there are some strong motivation from mathematics, which the idea was to deal with a certain kind of algebra, which are the type 3 algebra. And if you want to build a usual spectral triple for type 3 algebra, it doesn't work. And so they explain that if you do instead this twisted version, then it works for type 3 algebra. And they also explain that it makes sense mathematically. So by twisting the commutator, you are not losing all the mathematical structure. I mean, everything works very well. So this was purely mathematics, okay? And what we realized, so starting with ID with Fedele, Lizzi, with Agostino, and then we move on that with Agostino, that using this twist, I will say that in the next slide, using this twist, we can generate this extra field, okay, that we cannot have with the usual commutator. Before saying that, I just would like to state a result that we obtained with Gianni Landi to say that this twisted spectral triple, they are compatible with the real structure that has been introduced much before for usual spectral triple. And basically all the formula that we have seen, so the covariant operators, the universal one form, and the first order condition, you can naturally twist them. Basically, you put everywhere a twisted commutator. And it seems, again, it seems artificial, but we made some work with Gianni and we checked that it's completely coherent. Okay, there is a natural way to twist all the formula and to make this twist compatible with the real structure. So basically, you replace everywhere the commutator with a twisted commutator. And so you've got this new formula for the covariant operator. You've got new generalized one form, and everything works well. So now, what are the applications to the standard model? So here, I would like to take the opportunity of this conference to just give a little bit more details, because we realized that we made various attempts, and at the end with Manuele, I think we've got the right one, but then we discovered that there was some trouble in the early attempts. So the early attempt that we made with Agostino Devastato and Fedele Lizzi was to somehow we wanted to be more conservative as possible, and we said, okay, if we want to generate this extra field, we just need to twist one part of the algebra, not the full algebra because it looks too complicated. And we just, okay, it's enough to apply the twist just on the part of the algebra that acts on the particle subspace of the finite dimensional Hilbert space, okay? And the point of, okay, here I've written the C is a complex number. So it is an element of I recall you that the internal algebra is C plus H plus M3. So let's forget about H plus M3 because here everything works well, but the point was really for the C part of this algebra. So we take a complex number, and this complex number, it acts on the subspace, finite dimensional part of the Hilbert space is divided into one which corresponds to particle and one that corresponds to antiparticle. And the fact that this C is a complex acts on both sides. So this is what I've written here. And here the 1, 2 means that we act on spinors. So this 1, 2 means that the complex number acts by multiplication on the right and left component of spinor in the same way. Okay, this is important because when we make the twist, this is precisely where we will play with that. So this complex number acts on the right and left component of spinors on the particle side and the antiparticle side of the internal space. And when we make the twist, the idea is to say we double the algebra. So instead of C, we take C2. And so we make each of this copy of C acting independently on the right and the left component of spinors. So this is what I have written here. So we take an element of C2, which is CR and CL, two complex numbers, and we make them act independently on the right and the left component of the spinor. But we do that only on part of the finite dimensional Hilbert space, the one that corresponds to particle. On the antiparticle part, we did not double the algebra. We do not apply the twist. And we just say we have to identify the C, which is here, with one of the two C, which is now here. And we can choose that was independent. We choose to identify with CR, for instance. And now what is the twist? The twist is just to exchange. It is an automorphism of C2. So we just exchange the two components. So CR and CL become CL and CR. So the twist, but we do that only on the particle part. So we obtain this thing. So you take this formula here and you change R with L just here and you obtain these things. The problem that it is not the same as switching the two components here because there is this one which is not modified. Here, the third complex number here is identical to the first one. And here, the third complex number is identical to the second one. So this is a bit technical, but the idea is to say in this model that we made, we were not making an automorphism of the algebra. We were making an automorphism, a change of representation of the representation of the algebra. And this small computation here shows you that it is not the same. If I exchange my two numbers here in the algebra and then I make the representation, it's not the same as making the automorphism that we have made here. And in the paper with Agostino, we noticed that, but we somewhere at the end we say, okay, it is an automorphism of the represented algebra. But actually, that's then turns out to be a problem because it is not really a twisted spectral triple in the sense of cone. Because in the sense of cone, the automorphism should be an automorphism of the algebra before you represent it. So here there was a kind of trouble, but we say, okay, we could I thought we had a solution with the work we made with Gianni Landi, in which we show how we can systematically associate it to a graded spectral triple, a twisted partner, using the grading. Okay, because using the grading operator, the grading has a good idea to split the Hilbert space into two subspace in which the algebra act independently. So now you can say, okay, if the algebra acts independently on two subspace, I can take two copies of the algebra and make one copy act on the first eigenspace, the second copy act on the second eigenspace. And that's what the whole idea, to say if we've got a twisted graded spectral triple, we can double the algebra. So instead of A, we consider A tensor C2, which is the same as A plus A. And we make each of this copy of A act independently on the eigenspace of the grading operator. And all the rest is untouched. So this is a minimal modification in that the Hilbert space, which is the Fermionic content of the model, and the Dirac operator are the same as in the standard model. And by doing this, we show that there was a possibility to make this work. So we built a twisted spectral triple, and everything is nice. And we applied this with Manuele to the standard model. And my hope was that, okay, it will give us the problem, it will solve the problem we had before, that we had with Agostino, to just twist one half of the model. What Manuele discovered after many computation, that in that case, this is the result we show with Gianni, that one of these conditions, this twisted first order condition, is automatically satisfied if we make this what we call the twist by grading. But if we apply this construction to the standard model, actually it does not solve our problem, because it does not give us this extra scalar field. Again, the extra scalar field twist commute with the algebra, and it is not here. And so that was a bit annoying, because we have, let's say, an automatic version, a systematic way to associate a twisted spectral triple to a usual spectral triple. But if we apply this to the standard model, it doesn't do what it is supposed to do, to generate the extra scalar field. And so what Manuele discovered, that actually we can do exactly the same kind of construction, but instead of using the grading operator, we can be a little bit more flexible, and instead, so the grading is gamma 5 tensor product with the grading of the finite dimensional Hilbert space. And instead of that, we can use gamma 5 with another operator, which is not a grading of the finite dimensional Hilbert space. It satisfies almost all the property that the grading should satisfy, except that we do not ask that it anti-commute with the Dirac operator. And if we do that, all the construction here works very well. And we found with Manuele a good operator which satisfied all this property and allows us to twist the standard model to generate the extra scalar field. But now there was a problem that the first order condition, which is one of the axioms of non-commutative geometry, this first order condition was no longer satisfied. But fortunately, there was some work from Walter and Cohn and Shamseddin about how to make fluctuation without the first order condition. And so this forces us to work out fluctuation in the twisted state without first order condition. So these are the work we made with Jacopo Zanchetin. And so actually it works well. And so we make the full model and we obtain this version. So in that case, we obtain the standard model. So now just for the 5 minutes, let me talk about what is the link with Lorentzian signature. So if we define these two operators, Walter has shown that there is a gauge transformation in non-commutative geometry, which actually can be summarized by this way. You take an operator and you act in the usual case. So without twist, you act with u and u minus 1 on your Dirac operator, and this gives you a gauge transformation where u is an element which is given here, with small u is a unitary element of your algebra. And of course, a gauge transformation, a gauge fluctuation in the twisted case, it preserves the self-adjointness of the operator. If dA is self-adjoint, then this operator is self-adjoint. In the twisted version, what we have shown in a paper with Fedele and also Sean Farnsworth, that there is a twisted version of a gauge transformation, which is given by here, but here the action of the unitary is twisted on one side, and so it does not preserve the self-adjointness. And the point that, okay, you can say, okay, it is a bit annoying, it is a lot annoying that the Hilbert space, that the operator is no longer self-adjoint, but the possibility is to say, okay, my operator is not behaving well, so I can change my notion of self-adjointness. So I will change the inner product. And since you've got a twist, if the twist is given by the action of a unitary, so which is written here, so you can define a new product just by taking the whole product of your Hilbert space, which is a bracket here, and you put the unitary that generates the twist, if it is an inner automorphism, you put the unitary that generates the twist in the middle of this product. This defines a new product that we can call the row product. And the good point that if, here I've got just an example, if you take for a manifold, so you twist a manifold, so you take the standard spectral triple of a manifold and you multiply by C2, so here you've got the action. So we act independently on the right component of spinor and the left component of spinor. and we make the whole construction, and you find that this new inner product is actually the prime product for the space of spinors in Lorentzian signature. So we start from something which is Euclidean, the Euclidean spinors. We make the twist, and we see that the twist, which is induced actually by the adjoint action of one of the gamma matrices, gamma 0, and it naturally defined a new product on our Hilbert space, which is a prime product. So it is Lorentzian signature. So one can say, okay, yeah, but it's okay. We've got a Hilbert space. You can put artificially a Lorentzian signature, but for physics, it's not enough. So the idea is to say, okay, look at what happened for the action. And there is another novelty that if you make this fluctuation, here it is purely commutative, and if you make this fluctuation of the metric, it is well known that in the commutative case, there is no fluctuation. They are all zero, they cancel. But if we are in the twisted case, they do not cancel. There is a new field which appears, which is this one here, which is a one-form field, okay? And it turned out that if we compute, so, okay, here I will go fast. There is a fermionic action, and if you compute the fermionic action for this double manifold, what you find in this thing here, and you can compare it to the Weil action in Lorentzian signature, which is given here, and you find that the two things are almost the same, except that there is a derivation in one direction, the temporal derivation, which is here, d0, which is not present here. But instead of the d0, you've got the sum of the component of this new field that we obtain here, the f0 component. And so if you make the assumption that this new field actually is the energy momentum of our fermion, so you make this identification here, you find that the fermionic action that we compute within spectral triple, it just identify with the Weil action in Lorentzian signature. So actually here there is some technicity because you don't have enough degrees of freedom to identify the spinors on both sides. So you have to double the manifold, okay? And here now you make the computation and you find exactly the Weil action. But the nice thing is that there is also a spectral triple, not for the standard model, but for QED, for electrodynamics that had been made by Walter and some students. And so the algebra is here. And if we apply this twisted procedure to this spectral triple, what we obtain with this fermionic action is precisely the Dirac action in Lorentzian signature. Although we start with Euclidean signature, okay? So now the work is in progress to do that also in the standard model, okay? So we hope that the fermionic action will give us also the fermionic action in Lorentzian signature. So here, just to summarize, the same process that turned the Majorana mass of the neutrino into a scalar, that was the initial motivation. It also generates a new one-form field, so this F mu, which, at least in the fermionic action, can be seen as the zero component of the energy momentum in Lorentzian signature. Of course, the problem is the spectral action, because the fermionic action gives you the action for fermion, and there is a spectral action which gives you the action for the boson. Here it is most tricky because since the operator is not self-adjoint, you cannot easily take the asymptotic expansion of its space. So here there are various people who are working on that, various attempts. So for the moment, I cannot say more about that. Of course, that would be the nice things to see what happened to the spectral action and to this. Is it really the energy momentum that we have? Does it still, this interpretation, does it still survive in the spectral action? And okay, just to finish the last minute, so I would like to advertise a bit my collaborator. So here are various papers, and well, let me advertise in particular Emanuele, which made all this computation in the standard model. And since he's finishing his postdoc in Genova, I would just like to say that if some of you receive some email of him looking for postdoc, so please pay attention because he's a very nice guy and he comes from physics, so he knows how to speak to phenomenologists and he knows also the math, which can be very useful to in our framework to talk to particle physicists. Okay, so we finish here. Thank you.
Sure. Okay, thanks. First, let me understand the sigma field that you is missing, which is just the Higgs field, right?
It's another scalar field. I mean, there's a model in particle physics that if there is a new scalar field that couples to the Higgs in a given way, then it allows to put the mass of the Higgs heavier, and then you avoid the fact that the potential of the Higgs field is not the Mexican hat, but actually it goes down to infinity. With the actual mass, the potential has this problem.
Yeah. Well, as far as I remember, in the Lot-Con model, it was already in the broken phase, right?
Well, in the Lot-Con model, you just have the Higgs. No, I don't think you've got extra scalar field in addition to the Higgs.
it had, I thought it was formulated in the broken phase. No. Anyway, my question is this sigma really the Higgs field? I mean, if you have a linear realization of the Higgs effect, you have the remaining degree of freedom, which is probably your sigma. So this is part of my question.
George, sigma is the breaking of SU2 cross SU2 to SU2 cross U1, like the Petit-Salam. So it's, I don't know if you want to call it a sigma. If you want to call Higgs, it's in Petit-Salam you have two breakings. You go from SU2 cross SU2 to SU2 cross U1 with one field.
I see.
And then SU2 cross U1.
So it's not what we call sigma.
It's not the Higgs.
We call sigma in the sigma model, let's say. Or
no. Sometimes it's called rho, but then there are, so it's called sigma also in the literature, in physics literature, because rho is used for other things. So there are.
This was my
question. No, this is like is the field when you have Petit-Salam, no? So you have two breaking of the symmetry.
Yeah.
So you have is that field there?
So it's not the.
So it's a higher energy and
the remaining field of the SU2 cross U1 breaking.
No, then there is that one too that appears.
But this is not what.
No, it's not that. So it's not the one at 125 GeV.
Okay.
We'll have a higher.
And also for the other one, of course, to make statements if it is compatible or not, and so on, you need a calculation like what was described before. I mean, even for the Higgs, the real Higgs. Otherwise, for the real Higgs, which is not the sigma, but the Higgs field, to make statements about its mass and compatibility with physics and so on, you need a calculation as was described before. Because if you don't do that, you cannot make any statement about the mass.
Walter?
Okay, thanks. I had a question about this operator D you started with, that would be self-adjoint. And is that also Klein self-adjoint, or is it Klein self-adjoint after fluctuation? How does that work?
No, actually, it's none of this. Because, I mean, if you start with the Lorentzian Dirac operator, then it is Klein self-adjoint, but we don't start with this one. So when you make the fluctuation,
no, I mean with the R. You said with the R in the inner product, you improve the situation about things remaining self-adjoint.
Does not really improve it. Just saying to say, well, there is a natural inner product which is induced by the twist, let's say, and this turns out to be the Lorentzian inner product. But the operator we start with is not. No, it's not Klein adjoint with respect to this one, because it still have inside that we start with something Euclidean. Actually, in no places we obtain the Lorentzian Dirac operator. It's just through the action that we find something which is Lorentzian. And that was the idea, to say maybe we should not fight to find the Lorentzian Dirac operator, Klein adjoint or whatever, because it doesn't work. I mean, at least we did not manage to make it work. But at the end, what is important is not to have the Dirac operator Lorentzian; it is to have an action which is Lorentzian.
Yeah, but
and that's why we just say, okay, let's go to the Fermionic action. And at the end, it turned out that for electrodynamic, it works. So
yeah, okay.
The hope is that it will work
action,
also for the standard model.
But to write a spectral action, you have a problem since it's not self-adjoint anymore.
Yeah, because it's no longer self-adjoint.
Okay.
Once we make the fluctuation, actually, if we make the gauge transformation, it's no longer self-adjoint. So what we made with Agostino actually was to take the trace of D star D. But it is a bit, I think it's not the good answer.
What's self-adjoint?
We can compute something, but we are just losing everything we have made before by doing this.
Okay, thanks.
This is somehow a related question. I mean, for the twisted spectral triples, I mean, there's a procedure, there's a way to untwist them. There's a price to pay. Then usually when you start with a self-adjoint Dirac operator for the twisted spectral triple, then when you untwist it, you might get something which is not self-adjoint. But then maybe in this case, I mean, for this minimal twist or for the twist like that, maybe you get something which is Klein self-adjoint. I mean, what would you comment on that?
Yeah, we should look at your procedure to untwist. I mean, we have not looked at that. Yeah, that would be a good.
That would be something that links, you know.
Yeah. That's a very good idea. I mean, we haven't looked at that, but yeah, that should be
Thank
done.
you.
If you put together the fermion doubling, then pretty much this is what happens. Because this twist becomes the part of the Wick rotation to eliminate one of the two doublings. This is some work which I did with Francesco D'Andrea. And okay, I don't see other questions. I don't see questions in the chat or hands raised. Then the question of Andrej makes a smooth transition to his talk. Thank you again. And the next speaker is Andrej Sitarz. And that is the talk will probably come on the.
Should be right now. So I need to go back. Yes. Okay, so good morning.
Okay, the title is, I was looking for it and that arrived before that. Please.
Okay, thank you very much.
So 5 minutes, I will.
Absolutely. Yes, so thank you very much. It's great to be here in person and it's great to give a talk. Thanks to all your organizers, John and everybody. What I want to do is a sort of a version of and continuation of a different direction. I mean, so we saw the direction of, going towards the quantum theory in the talk by Walter. We saw the direction of going a little bit beyond the standard model and introducing some extra fields and going to the Lorentzian signature in the talk by Pierre. What I want to do is something, going into the direction of gravity. So modifications of gravity, I mean, sounds little bit dangerous because there are many, possible alternative gravity theories. But I want to see, I want to just explain, I mean, what happens if you try, to modify some of the things that people usually work with in this setup of non-commutative geometry. So first, a little bit of motivation. I mean, already a lot of has been said before. So what is the spectral geometry? So the principal idea of spectral geometry is that you don't work with a manifold, a metric, and fields on it. You still keep the manifold, you still keep the metric, you still keep the other constructions like the vector bundles, fiber bundles, but you work rather with differential operators, or more generally, pseudo differential operators in the context of manifolds. So you just, replace the idea that there are some fields to the idea that you work with operators on some sections of vector bands, operators on something, on functions, whatever. The typical example, and this is, this necessary bit of mathematics, is that you work with a Laplace operator. If you work with the Laplace operator that you have actually includes the metric. So you can have the metric sort of incorporated in the Laplace operator, but not only the metric. I mean, if you go to generalized Laplace operators, you can have the connection and you can have the scalar field, and that would be all in this type of, second order differential operator. And that would be, divided into several parts. So for instance, I mean, the metric would be this principal part. I mean, using this mathematical language of pseudo differential operator, principal part of this second order differential operator, then the connection and the torsion terms, possible torsion terms, if you assume your connection is has non-vanishing torsion, could be incorporated in this generalized Laplace, the next order part, and then the scalar field would be the zero order. So there's a very nice way to extract some geometric things from these operators using basically the ideas of the heat kernel expansion, so the asymptotic expansion coming from the spectrum. So sort of a nice thing if you take just the trace of the the heat operator, so e to the minus t
and Laplace operator, then you can get, I mean, in the scalar case, when you just use only the metric, you can get the volume. This is for the four-dimensional manifold, four-dimensional compact Riemannian manifold. And then you get this next leading term, you get just the scalar curvature integrate. Okay, so this is that one can sort of, maybe not equivalently, but nicely replace working with fields, working with geometry in this way by working with differential operators. Now, as you've heard, you know, the idea to use the spectral geometry has been around for some time. I think, you know, probably the earliest attempts were in somewhere in the 60s, and there's the work of Sakharov. I mean, that was all relevant to gravity. Then in the 80s, there was a lot of papers, a bunch of papers. I mean, computing this hit kernel terms for various modifications of gravity, including the Einstein-Cartan gravity, so the gravity with torsion, and so on and so forth. Then applied to non-commutative geometry by Kohn Shamsuddin, and then many other people I will not even, you know, try to name. This gives us a nice approach to describe both in classical terms and classical action gravity as well as particle physics. And we had about this attempts and this explanation of particle physics, including all the gauge fields and including the Higgs field. So the good thing is that when you take some easy examples of geometries, like the classical geometry, so manifolds, and some almost commutative geometries like manifolds, tensors, so products with some finite spaces or finite algebras, then the action is computable. It is actually computable in some more advanced examples. So for instance, if you take a non-commutative torus, if you take the Weyl space, even in case of some Q-deformed spaces, some things could be really computed and computed explicitly. So this is a good advantage. It's not only an abstract formula, but you can get really some numbers. And then we had it, you know, that in these things that are related basically to particle physics, these numbers really can be gotten. Now, there's one thing which is quite interesting, and this is a sort of a recent 2 years development. I mean, usually there's been a lot of complaint that this, you know, things like the hit kernel expansion are basically restricted only to the Euclidean case. Well, in case for the physics and for making the quantum theory, this is maybe not that bad. But anyway, you know, one usually says that one lives in the Lorentzian universe, and then is this possible for in the Lorentzian setup? And it actually appears that there's been a recent progress for computing the spectral action, actually, you know, in a very limited, you know, sort of range of operators, just the Laplace operators, scalar Laplace operators, but in the Lorentzian framework, and it really, you know, gives the same result. I mean, at least it is computable, and the techniques that come from the quantum field theory, algebraic quantum field theory, are actually applicable there. Now, what I want to just advocate is that there's a huge room for going a little bit beyond the standard model, not only in the direction of making the finite algebra slightly different, not only in adding some extra fields or making the spectral triples twisted, but also in modifying, you know, the usual setup of product geometries. So the typical thing is that's been presented in talks by Pierre and also by Walter, that when you go to this slightly modified geometries like the almost commutative geometries, you usually take the product, like the Kaluza-Klein, of a manifold with a finite space or finite algebra. And then what you construct the geometry on it, so the metric, the Dirac operator, as a product geometry. So it's like, you know, when you take the torus, the usual torus is the product of two circles, and just consider the geometry, the metric, which is just the metric on one circle, and the product with the metric on the other circle. But of course, more generally,
I mean, torus, when you make an arbitrary metric on torus, is not like that. It could be very asymmetric. Or on other manifolds, we can also have a metric which is not really of the product type. So the question is, what happens if you actually consider a very nice, you know, sort of simplified standard model, like the early toy model of Conlot, and you can relate this toy Conlot model, in fact, to some version of the models by John Mador, Dubois Viollet, and Richard Kerner when they consider the matrix algebra. I mean, this is something like when you take this finite space to be C plus C, so 2 points, this is like the diagonal 2x2 matrices. So you can embed it into the larger version of a matrix algebra, and of course you can go higher and higher, but this is just the thing. So all I want to just present the results are based on a joint work with Arek Bochniak, my PhD student, and there are basically 2 papers and 1 in preparation, which is just work in progress. So what happens when you just take it seriously and consider non-product geometries? I call it non-product geometries, but actually what matters is that these are non-product operators. So usually in this sort of natural attempt to create a geometry on the product space, you take Dirac operator on one space and a Dirac operator on the other space, or metric on one space, metric on another space. The thing is that in an aim to generalize it, you just generalize these things to be 2 different independent Dirac operators, independent from each other. So what does it really mean? So if you have this sort of image that this is like it's been always used like a 2-sheeted space, so like 2 universes, 2 4-dimensional universes, and the Higgs field is something which interpolates between them. Using the other words, I mean, this is we heard in the previous workshop, Humboldt colleague, I mean, like 2 brains, you know, and something like 2 metrics on 2 brains and some interaction. So this is, you know, the version using the differential operator. So what you consider as a differential Dirac operator on this 2-sheeted universe are 2 Dirac operators on each space and something, you know, which interpolates between them, which you interpret as a Higgs field. Okay, the standard Conlot model would be D1 equals to D2. But now, having this, there's a very nice question, how to compute? Well, just to compute, because we know how to compute using the language of and using the tools of the pseudo-differential operators. This is just a task to do. So to compute the spectral action and see what happens. So the question is whether what would be the interaction between those Dirac operators. So transferring into the case of metrics, you have 2 different metrics. What would be the interaction between those metrics? The second thing would be, well, is this some sort of physically viable model? What is this model? And the second thing is, I mean, is there some sort of mechanism? Is there a mechanism that would lead to what we observe? I mean, we observe just 1 metric. The idea would be that this matrix, I mean, since these Dirac operators are the Dirac operators usually that couple to the right and left-handed fermions. So, I mean, we would like it, you know, in the end to be something like that they are equal, or they, you know, tends to be equal. Now, the computation of this action is surprisingly, I mean, quite difficult technically. I mean, it involves, you know, really some integrals that are not known in general analytically. So either one can get to some simplified models, which are nevertheless realistic, or to the computations, I mean, numerically. But it's very nice that in the cosmological context of Robertson-Walker geometries, this is actually computable. So when you get the assumption that you have the metric, which is the Robertson-Walker type geometry, this is still Euclidean. So we still in the Euclidean setup, for any curvature that you can have positive, negative, or zero, and you can compute what are the terms. And the terms are as follows. So this is the action is just using the Wojcicki residue, the Wojcicki residue of the Dirac operator to the -4, the Wojcicki residue, the second term is the Wojcicki residue to the -2. You do the integral of the cosphere, and you just obtain first the usual Einstein-Hilbert action for each sheet of the universe. So this is the volume for the first part, the volume for the second part, the scalar curvature term for the first part, the scalar curvature term for the second, and what is most interesting, there's an interaction term, a quite complicated interaction term, which is this interaction term is proportional to the phi square. So just in case, when you have something like, when you have the interpretation of this phi, which could be a field, as a Higgs field, and which has a non-zero vacuum expectation value, then this interaction term between this matrix would be non-zero. And then you can just look at, is there a modified gravity theory that actually looks similar to that? And surprisingly, well, maybe not surprisingly, there is something which is called biometric gravity. When people consider one metric to be some sort of a background and another metric, and there's versions, of the theories of the theory, and there are some predictions, and there are some comparison with the observations. But nevertheless, I mean, is this just the same or is it different? It's slightly different, because here the difference is that, I mean, we have something like exactly two different metrics, but they are on the same level. In the biometric gravity, those metrics is like, one is sort of the metric, the other is like maybe some additional, degree of freedom. But still, nevertheless, the properties of this interaction term between the metrics are quite similar. So if you look at this potential, so here A1 and A2 are just the scale function of the Robertson-Walker geometry. B1 and B2 are this so-called Laps function, I mean, here in this metric. So if you look at this potential, it's utterly complicated, highly nonlinear, and when we later come to the equations of motion, I mean, this will create a problem, but it has some very nice properties. So for instance, if you look at how it depends on the metrics, I mean, it has certain symmetries when you, of course, switch the metrics. And generally, when you, in this case, in the case of the Robertson-Walker geometry, you can express it, well, as a rational function of so-called symmetric polynomials in the square root of, well, x, where x is just this one metric inverse times the second metric. So in the biometric gravity, they assume that the action is expressed in terms of the symmetric polynomials with arbitrary coefficients. What happens here, it's not polynomials, it's rather here in this case is a rational function. Later on we did some computation, this is the work in progress, that actually these are not polynomials, there could be some logarithm terms, there could be some more complicated terms, still expressed in terms of the symmetric polynomials, but this symmetric polynomials, but the symmetric polynomials, I mean, then they really play a part in some more complicated functions like rational and then logarithms. And this biometric gravity models, I mean, this is the reference for Hassan-Rosen. So having this potential, we can ask whether there is some physics behind it. So what happens if we put it into the equations of motion? So just the cosmological equation of motions. And of course, when you have this equation of motions, just general, put it like that, I mean, this is basically not possible to solve because they are highly nonlinear. So what we did, we just checked for the stability of solutions. So stability of solutions, we just take the usual solution of the Robertson-Walker geometry, and then we look, after the Wick rotation, we look whether the small perturbations, So a small perturbation is just that we take both the scale functions to be standard solution of Robertson-Walker and small perturbation, and the lapse functions could be, because of symmetries, could be made to one lapse function. So then we obtain the linearized equation of motion, which we solve. And then we check whether these solutions are stable. So it simply means that whether some small perturbations in the Robertson-Walker geometries would, tend to zero. So these deviations would tend to zero. So the solution will be stable. And there I will just, show you two examples, and there's more in the papers that I've shown, in the literature that I've shown. So if you consider, for instance, the empty de Sitter universe, then there's a region of parameters. I mean, this is, something, at the moment, I mean, this is rather qualitative, analysis, and then later on one can pass to some sort of more quantitative analysis and, plug in some numbers. But there is a region where the dependence is really exponentially damped. So the dependence on time on this t parameter of the perturbation is exponentially damped. So it simply means that whatever, small perturbation at the early stage or at some stage of universe between those two metrics will be, then it will be exponentially damped and will get in the end the product geometry. Another thing quite interesting, so we checked several models, so empty universe, matter-dominated universe, radiation-dominated universe, and some other example. So for instance, in the radiation-dominated universe, I mean, the solution is the combination of Bessel functions, so certain Bessel functions. And interesting thing is that, for instance, I mean, this is the lapse functions will diverge at the early age of the universe, but the scale function will be quite regular. So it simply means that, I mean, you can start from zero lapse function perturbation, infinite, zero scale function perturbation, infinite lapse function perturbation, and still, arrive at the product geometry in the variant. Finally, it's interesting to, I mean, comparing it to the biometric gravity models and comparing it to other modifications of gravity, it's interesting to see how it actually looks for the small perturbations of the metric. So what do we assume? We assume the flat metric and the small perturbations of the flat metric, and just we try to derive what are the terms that you get from the action in the perturbative expansion in the small parameter epsilon. And then exactly, I mean, like in the biometric gravity, what you get, these are the just symmetric polynomials in this metric. So basically in the difference, so the potential in the first term is proportional to the trace of the square of the difference of those perturbations. Then you get some extra terms. The thing is that in biometric gravity models, so in general gravity models like this, those coefficients here, so coefficient here, and so on and so forth, are arbitrary. Here, the power of the spectral action, the power of this derivation is that those coefficients are fixed. So there will be one overall coefficients, but the sort of the terms that you get, I mean, are later on are fixed. So this is not arbitrary, and this is, to be compared later on with what they get and what are the limits, what are the proportions that are sort of admissible by observation. So to sum up, when you look for the non-product geometries, so geometries that are not actually of this product type, so when you take this, what Pierre said, I mean, this Dirac operators to be Dirac operator for one plus tensor identity plus maybe gamma, the Dirac operator for the second thing, you get something which is a little bit, possibly more interesting. And this is the way, to expand, to go beyond maybe what do we know. And this is both in particle physics. I mean, another side thing is that when you actually apply it to the particle physics, you get something to the standard model. You get something that with no fermion doubling, you get a nice explanation of the CP violation and so on. Doesn't satisfy all the axiom, but this is nicely explained. There's an interesting thing that these biometric gravity models are linked to this approach. And there's also an interesting thing that, you can arrive at these two metric models from different angle. I mean, looking at the, for instance, at the action and at the gravity and whatever approach on the Q-deform spaces on the Moyal. So this has been the work by Patricia Vital, Marco de Cesare, Mary Sekerediu. And it is quite interesting, to explore it. Of course, then later to explore it for the full standard model, so for the full, not really easy algebra, which includes quaternions and 3x3 matrices, and just to apply it for that. But the bottom line is that one should try to explore, one not should be intimidated that, going beyond product geometries is wrong. Going beyond product geometries is quite natural, and there might be some interesting and possibly physically viable models. So thank you very much. I think I am more or less on time. And this is the bottom line. I will just use one more slide to advocate and advertise for the special issue of Journal of Physics A, Non-Commutative Geometry and Physics. Everybody is invited to submit their contribution. Thank you very much.
Thanks. The questions? You saw a question which I didn't see. Okay.
Have you checked whether it's ghost-free, this action? As you know, the usual biometric theories have a 4-parameter ghost.
Yes, yes. So no, we haven't. I mean, this is the thing to compare with the biometric theory. It is quite involved. I mean, we have the so to say explicit formula for this Robertson-Walker geometries. We go slightly beyond it with some slightly little bit more freedom in the construction of the metric, but still diagonal, and then we get logarithmic terms and so on. But the action is rational in this sort of invariant terms, and this is not polynomial, and they assume polynomial. So I think this is the work in progress that we have this linear perturbation which could be done explicitly, and then we can compare the expansion in the symmetric terms that we get with the assumptions by biometric gravity, and then we can compare the coefficients, and this then it will be possibly feasible to answer the question whether these proportions of parameters correspond to the parameters in the biometric Hazen-Ross and biometric gravity that is ghost-free. So this is
somehow the structure of Gabadadze and de Ram and company is very simple. It's generalized cosmological terms with different Vierbeins. So you don't see this emerging in any natural way here.
Oh, I mean the structure here is. There's also the question of interpretation, because this is like really playing with two manifolds. So the both metrics are on the same level. So this is slightly probably different.
I don't think that's important.
Okay, so yeah, yeah.
Okay. If there are no more questions on behind me, we can thank again the speaker. And we reconvene at 11:30.